All right, so this video is on using U-substitution as a method of integration. So U-substitution, using U-substitution to integrate. All right, so the way U-substitution works is we say if we have the integral of f prime of g of x times g prime of x dx, then we're really integrating f prime of u du, where u is g of x and the derivative of u is g prime of x. So I'm going to go back and kind of explain what this is. So if we have f prime of g of x times g prime of x, this right here is the chain rule. So I'm saying I took the derivative of something that had an inside, and then I had to multiply it by the inside. So if I reverse that process, then I'm going to let the u represent the inside, and I'm going to let the du represent the derivative of the inside. And then when I take my integral, I can really just integrate f prime of u. And then I'll put my plus c, and then I can go back and I can plug whatever it was for u back into the problem. So this is really a formula. When you remember U-substitution, you were probably never ever going to look back and remember it this way. You're just going to remember it based off of like how we actually do it. So we're going to go through and just do some examples because this is really something you have to learn through trial and error. So the instructions are just going to tell you to integrate. And it will be while you are integrating that you'll say like, that function looks like it has an inside and an outside, and that's how you'll know that what you're doing needs to have U-substitution. So if I look at this example, I can see that my function has an inside and an outside. So on the inside, I see this stuff. So I'm going to say that u plus x squared, and the derivative of u, derivative of 1 plus x squared, is 2x. So that means that when I do this problem, that's 2x times the derivative of x. All right, so when I do this problem, instead of saying the integral of 2x times the square root of 1 plus x squared, I'm going to say this is the integral of u to the 1/2 power times du. All right, so I'm going to show how this includes everything that we had. So the u, we have the square root of u, the u represents the 1 plus x squared, so that part is included in here. The du represents the 2x, which was in the front, and the dx, which was on the end. So the u is the stuff inside, the du represents the 2x and the dx. So this represents everything. All I did is I just rewrote it to the 1/2, so it'd be easier to integrate. So now I can go ahead and use my integration rules. I'm going to add 1. So that gives me u to the 3/2 divided by 2/3 plus c. And then I'll go ahead and I will flip that back up. So that's 3 over 2 u to the 3/2 plus c. And now I can go ahead and replace u with what I took out in the beginning. So I'm going to say 3 over 2 times 1 plus x squared to the 3/2 plus c. And we know we could write it like that, or we could write it with a radical, either way. And if you ever want to double check your answer and make sure it's right, then you should just take the derivative of this and make sure the result gives you that. Okay, for this one, we're going to integrate x to the 3rd cos of x to the 4th plus 2 dx. And so again, I have to think about what's inside and what's outside. The inside would be the u, the outside would be the derivative of that. So I'm going to say u is x to the 4th plus 2. and that means that du is 4x to the third dx. Now, what I notice here is that this problem had the x to the third, but it did not have the 4. So that means that I'm going to go ahead and I'm going to divide by 4. X to the third is what I really had. So I'm going to go ahead and rewrite this problem. So I have the integral of cos u times du over 4. That's basically the problem that I'm doing. But du over 4, I'm not going to leave it like that. That'd be kind of weird to work with. And so I'm going to go ahead and I'm going to take that 4 and pull it out to the front, which I will do in a second. But I want you guys to see how this represents everything that we're talking about. So cos u is cos of the x squared plus 2. The du over 4 represents x to the third and the dx. So du over 4 is x to the third and the dx. And that gives us everything. Okay, so just like I said, this du over 4, I'm going to take that and pull it out as a 1/4 in the front. So I've got 1/4 times cos u du. The derivative, the antiderivative of cos is sine. So this gives us 1/4 sine u plus c. And then we can go ahead and we can replace the u with what we had taken it to represent in the beginning. All right, number 3. So here we have the third root. We're taking the integral of the third root of 2x plus 1. I don't see an outside, but I do see an inside, so I know I have to use U-substitution. So I'm going to go ahead and set up the problem. I see that the inside is 2x plus 1. I can see that the derivative of the inside would have been 2 dx. Now, I don't have a 2 on the outside of this. I only have the dx on the outside of this, so that means I need to divide by 2. So if I write the problem that I'm going to be working with, it's going to be the integral of the third root of u du. And so we've got the third root, here's the u right here. And then the du, and it's actually du over 2. The du over 2 represents the dx. So just like before, I'm going to take that divide by 2, I'm going to pull that out as a coefficient of 1/2. And I'm going to rewrite this instead of third root of u, I'm going to call that u to the 1/3. So I'm going to go ahead and add 1, that's 4/3. So I have 1/2 u to the 4/3 divided by 4/3 plus c. So that's 1/2 times 3/4 u to the 4/3 plus c. And then I can go ahead and multiply those fractions in the front to give me 3/8 and replace the u with what I had, which was 2x plus 1 to the 4/3 plus c. All right, here is our fourth example. We are going to do the definite integral from 1 to 2 of 1 over 3 minus 5x squared dx. And so I know that u is 3 minus 5x, and I know that du is negative 5 dx. And I can see that when I look at this problem, I do not have a negative 5 in the front, so that means I need to divide by -5, divide by -5. And so that means that the integral that I'm going to work with is 1 over u squared times du over -5. And I can go ahead and rewrite that. That's going to be -1/5 in the front, and then u to the -2 du. And if you notice, I haven't dealt with the fact yet that my integral is a definite integral. I'm making it look like it's an indefinite. So this is in terms of x. This 1 and this 2, those are in terms of x values. I cannot use 1 and 2 if I'm writing my definite integral in terms of u instead. So that means I need to translate these into u's. So if u equals 3 minus 5x, then u of 1 is going to be 3 minus 5 times 1, and u of 2 is going to be 3 minus 5 times 2. So we have 3 minus 5 is -2, 3 minus 10 is -7, and so the 2 was on top, and so the -7 is going to go on top. The 1 was on bottom, so the -2 is going to go on bottom. So when we rewrite these, we don't care which is smaller, which is bigger. We're replacing them exactly where they belong. All right, and then I can go ahead and I can do the problem just like I would have. So I'm going to say plus 1. So I've got -1/5 u to the -1 divided by -1, and there's no plus c. I'm just saying I'm evaluating this from -2 to -7. And I can go ahead and simplify this a little bit. -1/5 divided by -1 is +1/5. I have a u to the -1, so that means that should be on the bottom of a fraction. So that's 1 over 5u. And this is being evaluated from -2 to -7. And so I'm going to say 1 over 5 times -7 minus 1 over 5 times -2. And that's going to equal -1/35 minus -1/10. And I could do that by hand, but I'm going to go ahead and just say it's 1/14 in a calculator. Now, it is possible to do the same problem and not finish the problem with u. It is possible to go ahead and integrate, say that your integral is 1 over 5u, and then rewrite the problem in terms of x, and then use the original 1 and the original 2. It is possible to do it that way. In fact, when I did it on my paper last year, that's actually the way that I did it. So you can see I rewrote the problem back in terms of x, and then I evaluated it using 2 and 1. And the reason that I did not leave that in the video for this time is because as I went throughout calculus last time, I started to notice that some multiple choice questions were written so you had to do it this way. And if you didn't understand how to do it this way, you could not finish the problem correctly. And so that's why I'm showing you guys how to do it by converting your integral into being in terms of u. Okay, we're going to do that one last time. And then I think I'll leave the rest of the examples to do in class. So you guys can see another one using the U-substitution on a definite integral. So here's example 5. We're going to do the integral from 0 to pi/4 of sine of 2x dx. And so we use the u to represent the inside of the function, which is 2x. And then du is the derivative of u, and the derivative of 2x is just 2 dx. So if I look at the problem, I can see this inside, but I don't see a 2. So I'm going to go ahead and divide the 2 over. So that means that what I'm integrating is sine u times du over 2. So if I go ahead and rewrite that, that gives me 1/2 times sine u du. That's what I'm integrating. And then I need to go ahead and figure out the upper bound and lower bound of the integral by putting it in terms of u, so it's not in terms of x anymore. So I've got u of pi fourths is 2 times pi fourths, and u of 0 is 2 times 0. So this is 2 pi fourths, which is just pi halves, and 2 times 0 is 0. So when we evaluate our integral, we're going to do it from 0 to pi halves. Okay, so the antiderivative, or the integral of sine, would be negative cos. So we have 1/2 of negative cos u evaluated from 0 to pi halves. And so I can go ahead and write that as negative 1/2 cos u evaluated from 0 to pi halves, and I'll go ahead and just plug that in. So negative 1/2 times cos of pi halves minus negative 1/2 times cos of 0. Cos of pi halves is 0, so we've got 0 minus minus makes a plus. 1/2 times cos of 0 is 1, so that's 0 plus 1/2, which is just 1/2.